All right, how's it going? Welcome back to another video here in the series on group theory. So far, we have been doing a lot with the symmetric group, right? Which essentially is this group that describes the set of all possible permutations on a set of, in general, n elements, right? Or all possible reshufflings of those n elements. And we've been trying to understand this thing called the symmetric group. And the way that we have been understanding it is by understanding its elements, the individual permutations themselves. And in the last couple of videos, we introduced cycle notation to compactly describe a given permutation in the symmetric group. And if you remember towards the end of the last video, this is the main thing that I want us to have in mind for this video at least, is that we introduced these things called disjoint cycles, right? Where we have a given cycle and all of the numbers in an individual cycle only show up in one of them. All the numbers in here will not show up in here and vice versa. So we would say that this permutation is written in disjoint cycle notation. And when we write out a permutation in terms of disjoint cycles, then we can define something on that, or we can define a property of that permutation, I should say, called the cycle type. And that's what this sentence is right here. So we're saying that the cycle type of a permutation is simply the list of the cycle lengths when written out in disjoint cycle notation. So here would be an example of it where this is written in disjoint cycle notation, and we have a 3 cycle and also a 2 cycle, or a transposition, right? That's another word that we use to describe 2 cycles. So we would say that this cycle type is type 3, 2, because this is length 3, this is length 2, right? And, excuse me, while this is an okay way of describing a permutation or of classifying a permutation, there's definitely nothing wrong with doing this. You can probably imagine that there are going to be many different types of cycle types. We could have a type 3-2, we could have a type 4-2, a type 4-3. It really depends on how many elements are in Sn. And this isn't even assuming this cycle right here. This doesn't even assume that we're working in S5, permutations on 5 elements. We could be working in S6, a set with 6 elements, but maybe we just have a 1 cycle or a singleton that we're just not writing out. So as you can imagine, because there could be many different possible cycle types, this is a very broad, or I should say this is a very specific, the opposite. This is a very specific classification. There are going to be many different types of cycles, or cycle types I should say, for a given cycle. I'm saying the word cycle a lot, right? Now, the point of this is that there should be some other way of classifying permutations or elements of the symmetric group. A way that we can say whatever, if we have a sigma in Sn, whatever the permutation sigma is, we can say it's going to be, it's going to fall under one of a small number of categories. And that is going to be the motivation for this video, to say let's try to come up with a general classification scheme. And you can probably tell by the title of the video, what we are going to be doing is assigning a sign to a permutation, where a permutation, as we're going to see, is either going to be even or odd. And what's nice about that is regardless of what permutation we have, any permutation will fall under one of those 2 categories. And we'll see in later videos why there's also some motivation for defining a sign of a permutation in terms of looking at the even and the odd permutations. Okay. So hopefully that makes sense, and that's going to be the goal of this video, just to introduce what the sign of a permutation is. Okay. Now, there's a little bit of work in order to do that, in order to establish that, and there is a first result that we will have to establish here for a given permutation. So I'm going to erase the board, and then we're going to write out that first result and prove it next. Okay, so first thing that we need to establish in order to define the sign of a permutation is we need to first realize that every permutation can be written as a product of transpositions. And again, transpositions are just two cycles. Okay. So that's going to be kind of the first preliminary step that we need to establish. Now, hopefully, just even if the claim itself might sound a bit abstract, hopefully thinking about it intuitively might not be so intimidating. You can imagine if we are reshuffling many different elements in a given set. If we have a set of n elements and we're reshuffling those n elements, that if we were to break down the entire reshuffling process, say, okay, maybe we're shuffling a deck of cards. If we wanted to take that reshuffling of the deck of cards, you can imagine that we could slowly but eventually perform the entire reshuffle by just interchanging two cards at a given time. And essentially that's all this is saying. Any permutation, any reshuffling can be written as a product or multiple consecutive two cycles, multiple times where you're just interchanging two different elements. Okay, but let's actually go through proving this. So the proof's not very long too. It's almost just writing out in math notation what I've just said in words. So let's say that we have a permutation sigma in Sn, and we want to write out sigma in disjoint, or we've already established that any permutation can be written in disjoint cycle notation. That's what we talked about in the last video. So let's say that we do that. Let's say we have this permutation and we write it out in disjoint cycle notation. So maybe what I'll do is I'll say that sigma is, I don't know, maybe numbers A1, A2 through AK, and then B1, B2 through BL, and this could even keep on going, right? There's no reason why we only need two, a K cycle and an L cycle, but point is we're writing it in disjoint cycle notation, and we'll only go through this process for one of the cycles, and you'll see that it will apply to every cycle, every individual cycle in the overall permutation. So let's look at this first cycle, this K cycle, A1 through AK, and I think that we can almost just do this in one line, but I think the best way of verifying this is to go through a simple example afterwards. So if we have A1 through AK, it can simply be written as A1, A2, and then A2, A3. And this could keep on going all the way through AK minus 2, AK minus 1, and then finally AK minus 1, AK, like this. Okay. And this pattern would be applicable for every cycle in the permutation. Now notice too, you might be saying, well, now it looks like we're writing it and it's not in disjoint cycle notation, right? For example, we see that this cycle right here, we can be decomposed as having A2 in here, but A2 is also in here. And that's okay. We want to establish that early on, that the first way of writing sigma is in disjoint cycle notation. But we are decomposing it in a way where it is not in disjoint cycle notation, but rather is decomposed in a way where it's only a product of two cycles. Okay, so it doesn't need to be in disjoint cycle notation when we decompose it as a product of transpositions. Now, this might seem a bit abstract, so maybe let's just go through an example, a quick example to make sure that this makes sense to us. So maybe we'll just say we have a 4 cycle, 1, 2, 3, 4, and we can call this sigma. And let's just imagine acting sigma on each of these elements, 1, 2, 3, and 4. And hopefully this won't be, hopefully we're familiar with this at this point, that sigma 1 is going to be 2. It's going to go here. 2 is going to go to 3, 3 is going to go to 4, and 4 is going to go to 1. So I'll just quickly write that out. So that sigma 2 is going to go to 3, sigma 3 is going to go to 4, and sigma 4 is going to go to 1. Right? now let's apply basically this decomposition and show that we get the same thing. So we can also write, hopefully we have these in our head. Probably didn't even need to write those, but it's okay. We can rewrite this 4 cycle as a product of transposition. So we can write it as 1, 2, then 2, 3, then 3, 4. Notice that this is different than 1, 2, 3, 4. That the larger element in maybe the earlier transposition needs to be the smaller element in the following transposition. Okay. So because the 4 cycle 1, 2, 3, 4 is different than the 2, 2 cycle 1, 2, then 3, 4. Okay. So this is how we would decompose it, and maybe let's just imagine what this would look like. So sigma 1, and let's imagine 1 gets input into here. So 1 gets acted on by 3, 4. 3 and 4 aren't the number 1, so it's unaffected by this. It goes to here. The number 1 is not in here, so it's unaffected by this, so it also goes to here. And then 1 moves to 2. So sigma 1 is 2. Right? Now we can write out sigma 2 and do the same thing. So if 2 acts as our input, it's not affected by 3, 4. It is affected by this one, so 2 goes to 3. So now, after this cycle has acted on 2, we now have 3. And when 3 is the input into here, 1 and 2 don't affect it, so sigma 2 is just simply 3. And we'll do the last 2 just to be complete. Sigma of 3 would be acted on by the first one. 3 goes to 4, and then 4 is not in any of the other ones, so we just have that sigma 3 is 4. And finally, sigma of 4, we're going to see is going to get acted on by all of them. So when we have 4 as an input, 4 goes back to 3, so now we have 3. And now 3 goes back to 2, so now 2 is the new number, and then 2 goes back to 1. So sigma of 4 is just 1. And hopefully you can see how this idea would generalize to just a K cycle, and how if we can do this for one cycle, if we have a bunch of disjoint cycles, then we can do it for any of the cycles. So therefore, a permutation can be written as a product of transpositions. Okay, hopefully that makes sense. Now, that since we have established this fact that any permutation can be written as a product of 2 cycles, it turns out that we are going to use 2 cycles, so these transpositions, to help us define the sign of a given permutation, to effectively say whether this is even or odd. There's going to be a big theorem that we're going to write up now to show how to do that, so let's go through that next. All right, so we have arrived, I guess, at the main theorem of the video, and let's go through it together. It says, if we were to write sigma, some permutation in Sn, as a product of transpositions, then sigma will always be an even number or an odd number of transpositions. Okay? And we might be able to tell where we get the terminology for an even permutation or an odd permutation, but we'll get to that in a second. First thing, though, that I want to mention is that I made sure to say that sigma, not sure where I'm going here, let's go over here. Sigma will always be an even number or odd number of transpositions. So what I'm saying there is that when we write a permutation as a product of transpositions, it will always be even or always be odd. Now that might raise some questions, because we might be saying, well, isn't it just going to be even or odd? Why are there going to be multiple instances of being able to write a permutation as a product of transpositions in the first place? Let me be more clear. What I'm trying to say is that, let's say we have the same example that we had at the beginning of the video. This 1, 2, 3, 4, 5 type of cycle. And we could decompose this cycle in terms of a product of transpositions. This is already in transposition form, but this is not. So we could rewrite this as 1, 2, 2, 3, 4, 5, like this. But it also turns out that there is another way that we can write this same thing in terms of a product of transpositions. We could also write, let's do this, 1, 2, 2, 3, maybe 1, 3, 4, 5, 1, 3, like this. And all I've done going from this middle line to this bottom line is I have sandwiched 4, 5 in between two transpositions of 1, 3. And to see why this makes sense, hopefully let's first remind ourselves that disjoint cycles commute with each other. And that should make sense, right? If 1 and 3 are the only numbers affected by this cycle, and 4 and 5 are the only numbers affected by this cycle, none of these numbers are going to be affected by any of these numbers and vice versa. So it doesn't matter which order we apply them in. And we went through that last time. So we could take this, we could rewrite this as 1, 2, 2, 3, 1, 3, and swap 1, 3, and 4, 5. So then we get 1, 3 again, and 4, 5. Now, let's say that we are, whatever this, let's say this is sigma. Let's say that whatever sigma acts on, let's say sigma acts on the number 1 or the number 3, because that's the difference between this original line, 1, 2, 2, 3, 4, 5, and then this bottom line, 1, 2, 2, 3, two factors of 1, 3 before 4, 5, right? So the only thing new is these additional two factors. Let's say that we input 1 into this permutation. 1 doesn't get affected by this. Here, 1 would go to 3, and then 3 would go back to 1. So it's the same thing as if we just did not have either of these two in the first place, which is what we have right here. And same thing with the number 3, right? If 3 was the input, 3 would not get affected here. Then 3 gets acted on here, 3 goes back to 1. Now we have 1, and then 1 goes back to 3. So having two of the same transposition consecutively like this is effectively just not doing anything. It's the same thing as if we didn't write anything at all. Now, why am I saying all this, right? Well, the point of me saying this is that there are multiple ways, and this is not the only type of example too, but there are multiple ways that we can write a permutation as a product of transpositions. But what this theorem is saying is that regardless of how we write the permutation as a product of two cycles, whatever way we do that, we will always be writing it as an even number of two cycles or an odd number of two cycles. Like in the example we had right here, I think we started with 3 transpositions, 3 different two cycles, and then the bottom line had 5 transpositions, right? So it's still an odd number in that case. Okay. So I want to make that clear early on. That adds to the power of this theorem, that it doesn't matter how we write a permutation as a product of transpositions, that this will apply for any decomposition. Now let's actually get into the proof. So the first thing that I want to do is I want to define a function, and I'm going to define a function f, and it's going to map from elements Sn, or it's going to take elements from Sn and map them into the natural numbers. Okay. So it's going to take in a permutation and is going to spit out some positive number. Now what is that number going to be? So let's say that f acts on a permutation sigma. It is going to spit out the number of cycles that sigma has when written in disjoint cycle notation. So let's write this out. So number of cycles when written in disjoint cycle notation, when written in disjoint cycle Probably could have sped through this part, but whatever. In disjoint cycle notation, and we're going to make the claim that we're going to include singletons. Or in other words, we're going to include one cycles in this count. Include singletons. Okay. So let's go through an example really quickly to make sure we understand what this function f does. So let's say that sigma is this good old 1, 2, 3, 4, 5 cycle that we've been working with, and we want to compute f of sigma. So what we would do is we'd say, okay, let's take the permutation, and we will write it in disjoint cycle notation. In this case, it's already in disjoint cycle notation. So now it's just a matter of counting up how many cycles we have. Let's first say that we're working in S5, so there are only 5 different numbers that we could look at. Then we would say, all right, well, if sigma is in S5, then there are 2 different cycles that describe sigma. So we'd say that f of sigma is 2. Fair enough, right? Now let's suppose, though, that maybe sigma is in S6, so it is a reshuffling of 6 possible elements, but written in the same cycle notation. What that would imply is that even though, because 6 is not written here explicitly, that tells us that 6 is a singleton state. It is not affected by the permutation, but it is implied right here. Now, because the function, let me go over here. Because the function counts the number of cycles when written in this notation, including the singletons, so including these 1 cycles right here, we would just count up how many cycles we see. So if this was in S6, we would say, okay, well, I have 1, 2, and then 3 different cycles. So if sigma is in S6, then f of sigma is 3. Right? Hopefully this gives us a good idea of how to apply this function. Now, I should mention too that maybe just to go through 1 or 2 more relevant examples really quickly. Let's say that we're just working in Sn. So, and we have E in Sn, the identity element. Okay, and this will be important for later. So if we have the identity element, what does the identity element do? Well, it basically maps 1 to 1, 2 to 2, 3 to 3. It's as if we didn't reshuffle anything in the first place. So another way of writing E explicitly is just, if we're working in Sn, it's n different singletons. So it's 1, then 2, then 3, all the way through n. So then we say, okay, well, what is f going to be if we act on the identity element? Or in other words, what is f of E? We just count up the number of cycles, and there are n different cycles, so f of E is simply n. All right? Hopefully that makes sense. Now, one more example, because we're going to be working with transpositions, or these 2 cycles, quite often. Let's say that we also have a transposition, maybe 1, 2 in Sn. How can we really write out 1, 2 if it's an element of Sn? Well, let me just write that down here. We can say that 1, 2, if it's an element of Sn, is really going to be 1, 2, and then everything else is a singleton state. Right? It's a 1 cycle. So then we're going to have 3, 4, all the way through n. This is how we'd write it out in disjoint cycle notation. So then if we were to apply f on this 2 cycle right here, so maybe we're going to say f acts on 1, 2. We just count up the number of cycles we see. And we would have, basically if we had n here, it's almost as if these 2 just get combined together. The numbers 1 and 2 get combined together, so we have 1 less number of cycles than we did here. So f of any transposition is simply going to be n minus 1. All right. Hopefully this makes sense, at least how f is defined. Now, I think what I want to do is, because we're kind of running out of room here, I want to erase what I have so far, maybe just write out the definition of f at the very top to give us as much room as possible for the rest of the proof. So let me quickly go through that, and then we'll finish the rest of the proof out. Okay, so now let's just actually finish out the rest of the proof. So far we've been working with this permutation sigma, and we've defined this function f that counts the number of these disjoint cycles. What I want to do now is, let's say that we have our permutation sigma in Sn, and we want to multiply it by some sort of two cycle, some sort of transposition, which I'll call tau. And maybe we can say that tau is some two numbers CD which range between 1 and n, right? If sigma is an Sn. So if we have this, basically we want to see, or what our immediate goal is to determine what is going to be the value of f of sigma of tau, and we'll see why this is going to be important in a second. So what is the number of these disjoint cycles for this combined reshuffle? Now, to do this, hopefully it makes sense that if tau contains two numbers, c and d are going to be in between 1 and n, right? That they're contained within Sn, then that means that inherently these numbers c and d are going to be contained in sigma when sigma is written out in cycle notation, right? Because if sigma includes the singleton cycles, if we were to write out the singleton cycles, I should say, then we are going to be writing out n different numbers, regardless of how they are arranged in different cycles, right? Like whether we have, if we're working in S6, whether we have this 1, 2, 3, 4, 5 cycle, if we write it as 6, we're going to be writing out all 6 numbers in S6. So we're going to be writing out all n numbers for sigma in Sn. So therefore, we know that these numbers c and d have to be contained somewhere in this sort of sigma. Somewhere when we write it out in terms of cycles, it needs to be part of those numbers, is basically what I'm saying. The question then is that if c and d are written somewhere in the expression for sigma, where are they contained? Are they contained in the same cycle within sigma, or are they contained within different cycles within sigma? And maybe I shouldn't have erased this example. Let me just go back. I know I just keep going back to it, but if for example, c and d were the numbers 1 and 2, then if this was sigma, then we would say in that instance, 1 and 2 are in the same sigma cycle. But maybe c and d are 1 and 4. So that's the other possibility. Or 1 and 6, it doesn't really matter, where these two numbers are contained in different cycles. So those are the two possible cases that we're going to be interested in. And we just want to examine what happens with both of those cases. So let's look at the first case where c and d are in the same, that's an E, not a Y, the same sigma cycle. Okay. And if it's in the same sigma cycle, let's just say it's in some general cycle. So maybe we'll write C, and then A2, A3, all the way through AK minus 1. And then maybe we'll write D, it's at some later point. D, AK plus 1, all the way through AK plus L. So this is some cycle that's contained within sigma. C and D are both in this same cycle. And we're just writing this in a general way, where maybe we can start with C, and then after K different numbers, then D shows up. Okay. So this is this is what sigma. This is part of sigma, and let's keep in mind too, because sigma is in disjoint cycle notation, that even if we had other cycles besides just this one, if we were to then multiply sigma by tau, in other words by CD, any other cycles here cannot contain C or D. Why? Because it's in disjoint cycle notation. The numbers in here can't be the numbers in any of these other cycles. Whatever those cycles may be, if they even exist. So really, when we're saying that C and D are in the same sigma cycle, really all we have to do is we can say, let's just look at the specific cycle from sigma that C and D are contained in, and see how the number of cycles gets affected, because everything else is going to be unaffected. Okay. So hopefully it makes sense too that if we say that this is sigma now, or sigma tau, I should say. This is sigma tau, and we were to say what are the possible outputs for various inputs of this function, this permutation, then what would we get? And hopefully it makes sense that if we had pretty much any of these A values, we're going to get what we think we would get. A2, if we had sigma tau of A2, we would get A3. Sigma tau of A3, we get A4. Sigma tau of A4, we get A5, right? We just get the subsequent value. Same thing here. Sigma tau of AK plus 1 gives us AK plus 2, and so on, all the way up through A sub K plus L. So most of this is going to interact in the way that we think it would. We just need to really look at the cases where we have sigma tau of C or sigma tau of D, where C and D are the two inputs. So let's look at those. So let's say that C is the input to this permutation sigma tau. If C is the input, we say, okay, well then C first gets manipulated here. C maps to D, so now we have D, and then D goes to AK plus 1. So we can rewrite this by saying, if we start with C, remember C was our input, where does C go to? So C goes to D, D goes to AK plus 1. So then we're going to have AK plus 1. And then where does AK plus 1 go to? Well, just the next one, right? AK plus 2. And this pattern is going to continue, right? And it's going to keep on continuing all the way up through A sub K plus L. Oops. No, not all the way through A sub K plus L, like this. Hopefully that makes sense. Now let's just say we have the other input. We have D as our input. And actually, maybe just to make sure that we understand why it stops at A sub K plus L, let's say that A sub K plus L, this final element, is the input to this permutation sigma tau. So if we have sigma tau acting on A sub K plus L, it doesn't get affected here. It then moves to this cycle, and then it just goes back to the beginning, back to C. So then it goes back to C. And that's why we close off the cycle right here. Okay. Hopefully this is clear on how this product can get decomposed as this for the first input. Now let's just go to the second input, D. Let's say if we input D into sigma tau. Well, if we do that, D gets mapped to C. So now we have C as our input. And then where does C go to? C goes to A2. So for our next cycle, if we start with D, we say D, what's the next value? Then A2. And then the same ideas we had right here. A2 goes to A3. A3 goes to A4. This is going to continue all the way up through A sub K minus 1. Okay. So what we've essentially just done is we've taken this permutation, sigma tau, and we have written it. We've started by writing it like this, and then we have transformed it so it is like this. Now, why have we done this? So it's like, why do this in the first place, right? Well, the reason is because if we were to write sigma tau just like this first line right here, we see that C is in both of the two cycles, and D is also in both of the two cycles. So if we were just looking at the top line, we would say that sigma tau is not in disjoint cycle notation. So the reason why we are doing this, going from the first line to the second line, is to write sigma tau in terms of disjoint cycle notation. And notice that we've done that. All of the numbers in here are now different than all of the numbers in here. which are going to be different than any other possible cycles that are contained within sigma tau. So now we've officially written out sigma tau in disjoint cycle notation, and because of that, we can now apply the function f to it. Because, right, we need to have it in disjoint cycle notation in order to even apply the function. So let's do that. Let's figure out what now f of sigma of tau equals. Well, what we could say is that we might not know because it's so general right now, but let's suppose that we know what f of sigma is. So sigma has some value, f of sigma, like this. And what we can determine is that if we have some value for f of sigma, when we multiply tau on the right by sigma like this, notice that was the act of adding this, this transposition. I mixed the words of transposition and permutation off, but this 2 cycle right here. Basically what we have seen is that if we started with one large cycle in sigma, then sigma tau then produces 2 subsequent cycles in disjoint cycle notation. So it's whatever the value of f of sigma is, however many cycles are in, well, this one cycle and however many are before that, and then we see that by adding this, that gives us 2 cycles rather than just the starting one. So however many we had before we multiplied tau, plus the addition of 1. Okay? That is kind of the first key step. And again, this is kind of a long proof because this is still just for the first case. We need to go through the second case. So let me just quickly summarize this by saying if C and D are in the same sigma cycle, then this tells us that f of sigma tau equals f of sigma plus 1. All right. Let's now go on to the second case. Okay. So I want to make sure that we have, I'm just going to erase this bottom line right here. Even though we're getting low on space, the second case is really going to be clear, I think, if we have the first case already on the board. So for the second case, let's remind ourselves, the first case is when these 2 numbers are contained within the same cycle within sigma. The only other possibility is if these 2 numbers are contained within different possible sigma cycles. And what we are going to do is we're going to say, let's say that sigma, it's in disjoint cycle notation, but the only 2 cycles that we care about is the one that contains C and the other that contains D. Conveniently, we already have an expression for that right here. So let's say that, we'll write sigma tau, but let's say sigma can be written like this bottom line that we have right here. So let me just write this out real quick. We're going to have C, AK plus 1, AK plus 2, all the way through AK plus L. And then D, A2, A3, AK minus 1. I want to make sure that this makes sense and that we can do this. If C and D are in different cycles, this is a general way of writing that just for sigma by itself. C is in one of the cycles, D is in one of the other cycles. Hopefully we remember too that when writing out cycles, we don't need to have there's no necessary requirement to have like the smallest number first. So we can just put C at the front and D at the front of our cycle. Right? There's nothing inherently wrong with writing out sigma generally like this. Now when we multiply tau, that's when we need to also include this CD transposition at the very end. Okay? So the first 2 are sigma and the last one is tau. And the overall product is sigma tau. Now we want to do the same idea. We want to see how F acts on sigma of tau in this case. And in order to do that, we need to write out sigma tau in disjoint cycle notation. Say, okay, well, what we can do is we can conveniently use what we've already had in part 1. Because let's remind ourselves what we have here. In the first scenario, the same line, C a sub k plus 1 all the way through a to k plus L, and then D a2 all the way through a k minus 1. That is what we have right here. In this thing, the bottom line of case 1, this thing is equal to a single overall cycle and then the transposition CD. So I'm just going to make that substitution in for here. This, let me even just underline, this thing is equal to this with another factor of CD. That's what we established in part 1. So I can write this out as this first long cycle, C, A2, A3, all the way through A, K minus 1, and then D, A, K plus 1, all the way through A, K plus L, then the transposition, CD, space those out a little bit. And that's just what the underlying part was. That's what we equated to the underlying part. But we still had this additional transposition after that. So we still had another factor of CD here. So we immediately know we can use our part 1 results to establish what sigma tau is going to be like this. Now I might say, okay, cool, but this is still not disjoint cycle notation. I have C's here and I have D's here. Well, what did we just talk about earlier when we have two transpositions multiplied by each other, right next to each other? It's like the act of just not having anything at all, right? We can effectively just remove this, because if we have C and D as inputs, it's going to be the same as if we didn't include these. And that's kind of what's really neat about this, is because now sigma tau, if C and D are in different cases, different sigma cycles, we have seen that we can rewrite it in disjoint cycle notation as a single cycle. Let's keep in mind what this implies for us. Because, again, we want to remember that the goal here is to figure out what the value of f is as it acts on sigma tau. That's what we did for the first case. Now in the second case, what is f of sigma tau? And I hope we can see this. Actually, you know what, let me write it over here. I'm not sure if we can see this. F of sigma tau. Well, we want to write it just like this top case right here in terms of f of sigma. So it's going to be, make this a little bit, let's see this, f of sigma tau. We're going to relate it to f of sigma. Now if we had sigma by itself in the second scenario contained this first cycle and the second cycle, the two cycles that are underlined, and then any other disjoint cycles contained in sigma. So we have seen that when we start with two cycles with just sigma, then after we apply tau, getting it down to disjoint cycle notation takes us from two cycles down to one cycle. Or in other words, one cycle less than what we originally started with. So in the second case, f of sigma of tau is going to be however many cycles were in f of sigma, but one less than that. So it's going to be f of sigma minus 1. And these are the two possible cases. Okay. Lots going on, right? Again, if this feels abstract first, I don't blame you. It is. But that's kind of part of the usefulness and the power of this. If any step is confusing, though, definitely feel free to pause the video. That is the advantage of watching these videos on YouTube, right? Is we can pause, rewind whenever we feel like it. All right. I am definitely out of room, so I am going to erase most of this and just write out the summary result. If we have the case where they're in the same cycle, this is the result we have. If they are in different cycles, this is the result we have. And then we'll finish off the proof with the remaining part of the board that we have left. Okay, needed to make sure that my phone wasn't out of battery there, basically. We are almost done. almost done with the proof, right? And admittedly, this is a long one, right? But I think the longer the proofs are, a lot of times that means the more interesting they can be. And we're almost done. So let's just finish out the proof, and this will be the last thing that we do pretty much in the video. Again, where the main goal is eventually to establish what the sign of a permutation is. So really what we've done so far is we've said that if we have some permutation in Sn, regardless of, or if we have a permutation in Sn and then we multiply it by some 2 cycle, some transposition, regardless of whether or not they're in the same cycle, whether or not C and D are in the same sigma cycle, or if they're in different sigma cycles, we see that the act of multiplying sigma by a transposition, and this is the main general idea, the act of taking a cycle, multiplying it by a transposition, will give us however many cycles we already had, either +1 or -1. Now, what that means though is that is going to just change the sign of whatever sigma and tau, or what am I saying? That will change the sign of whatever we started with. If f of sigma was even, adding 1 or subtracting 1 will make it odd, and vice versa. If f of sigma is odd, adding 1 or subtracting 1 will make it even. Now, just to clear up maybe a subtle but still important point, is we've established in the previous video that when writing things out in disjoint cycle notation, aside from commuting cycles, like for going back to the same example of, we could say 1, 2, 3, 4, 5 is the same thing as 4, 5, 1, 2, 3, right? But aside from commuting individual cycles within a permutation, disjoint cycle notation is unique. And what is more, or the important part for what we're doing here is that regardless of if we're interchanging disjoint cycles, the number of disjoint cycles will remain the same. So we still have 2 cycles here regardless of how we interchange the order. And that's important because since sigma is in disjoint cycle notation, that tells us that there's only one value of f of sigma. F of sigma, regardless of what equation, or regardless of what case I should say we're working with, whether it's case 1 or case 2, f of sigma is guaranteed to have the same value, the same number of cycles in it. So really, even though these are different equations, one has a plus sign, one has a minus sign, they achieve the same overall goal of just the act of multiplying a transposition flips the sign, or whether going from in terms of being an even number or an odd number. Okay. Another way of writing this, and hopefully this will look familiar if we've worked with introductory number theory, specifically modular arithmetic, but we could say that in general, f of sigma of tau is going to be congruent to f of sigma plus 1 mod 2. That's just another way of saying that the sign gets swapped, right? And hopefully we've seen introductory number theory at some point. If we haven't too, it's not a huge deal. I'm telling you what this means. This means we're swapping the sign of the number. But I'll also link some videos that I've made previously in the video description. So what does this mean now? Because we've established a general result regardless of the 2 scenarios that we're working with. How do we tie this all together? Well, let's say that we have a permutation sigma, general permutation. And we have shown earlier in this video that we can write sigma as a product of transpositions. And if in general tau gets used to, if we want to represent a transposition with tau, let's just say that maybe it's represented by tau 1, tau 2, all the way through tau k, like this. So maybe we can write sigma as a product of k transpositions. But we've also seen that this decomposition is not unique. We could also write it as a different number of transpositions, a product of a different number of transpositions. So So maybe I'll say there's another way that we could write sigma, and I'll write this with tau 1 prime, tau 2 prime, dot, 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 through tau L prime. These could be different, and K does not need to be the same as L. And this is what I think is really cool about this, is that it doesn't matter how we take a permutation and decompose it. We're going to see that we are going to get the same overall sign, the same number of transpositions regardless. Now, how do we do that? Right? Well, what we can do, hopefully we know that by applying the identity element, that won't change anything. So I can apply the identity element right here, and we're going to get the same thing, right? And now we can construct sigma just by starting with the identity and then just repetitively multiplying each individual transposition. And we do it one at a time. And we already know the act, or we already know how multiplying one transposition is going to affect the sign, because that's what we've established. We've established this result right here. That's what we've spent the past probably half hour now doing. So let's do that. Let's start with this first decomposition right here. So if sigma, we start with E, that means that f of sigma is going to be f of E. What do we say f of E was? If sigma is an Sn, E is just n different singleton states, so it's going to be n. And then we just add on each of these different transpositions. For every individual transposition, we are adding the number 1 mod 2, or we are changing the sign one time. So if we have k of these, we're going to have n plus k, and maybe I'll say it's congruent to n plus k mod 2. In English, this just means that we are swapping the sign k different times. Now let's just go to this transposition right here. We also know that just another decomposition, another decomposition for sigma. F of sigma here is going to be starting with the identity, n, and then now we're swapping the sign L different times, mod 2. And since we're working in disjoint cycle notation, we know that f of sigma, like we mentioned, has to be unique. So n plus k mod 2 has to be congruent to n plus L mod 2. So then we can just equate the two. N plus k has to be congruent to n plus L. The only way that's true is if k is congruent to L mod 2. Or in other words, however many swaps of the sign going even, odd, even, odd, even, odd, this is telling us that we need to have the same number, or it will either always swap to even or always swap to odd. We need to swap to the same type of sign. That's what it means for these to be congruent mod 2. Okay. And again, just to summarize, this tells us that even if we make k swaps or L swaps, we're going to always have a positive, or I should say, we're always going to have an even number, or we're going to have an odd number. That completes the proof. It's a lot, right? But we've eventually got there. And let's maybe just read this to make sure we understand what did we just prove. So regardless of what permutation we have, then it can always be written as an even number or an odd number of transpositions. And now we get sort of to the grand finale, I guess, if you want for this video. How do we define the sine function? And maybe even pause to take a guess if you're not sure. Now, assuming we paused, or we haven't, the sine function is simply going to represent how many transpositions we have when a permutation is written as a product of transpositions. Okay, so maybe we should write it. I'll write it right here. Now, the sine function, by the way, is written SGN. I might be saying, why don't we write it SIN or something like that? And that is because there's the very familiar sine function from trigonometry, that whole opposite over hypotenuse thing, right? the wavy, the curvy thingy. So we already have SIN to denote that function. So we denote SGN to be a function that maps from the symmetric group into the set plus minus 1. And here's how it's defined. The sign of a permutation is simply going to be equal to -1 to some number. -1 to the L, maybe. I think that's how Dexter defines it. -1 to the L. Where L is the, where L is the number of transpositions, the number of 2 cycles that we have when writing out sigma as a product of 2 cycles. How do we write it out as a product of 2 cycles? We just shown it doesn't matter. So here's how you can tell the sign of any permutation. And that was the result, This should really be, maybe I'll put a star and a happy. Now, just to finish off the video, how do we tell the sign of a permutation? And how can you do this on some of the problem sets? And I think we're at the point where we can do problem set 2 at this point. I think we've got through most of problem set 1. What you do is you take a permutation, write it out in disjoint cycle notation, doesn't matter how you do it, and then just count the number of 2 cycles that you have, the number of transpositions that you have. If you have an odd number, then L would be an odd number, and then the sign of that permutation is -1. If you have an even number of 2 cycles, L is some even number, and then the sign of your permutation is +1. That's how you determine that is what the sign of a permutation is, and that's how you determine it. That is now the end of this video. Thanks so much for watching. I hope we were able to follow along. We are going to be using the sign of the permutation to be talking about some interesting concepts in the next video to finish off the section on the symmetric group. So thanks so much for watching, and I will see you guys in the next one.